All right. Hey, everybody. How are you? Well, happy Merry Christmas Eve. I know I hate to do this to you folks, but we lost today on Monday. Was it Tuesday? Because the recording didn't work. So, I'm going to go ahead. I'll record the video today. Please watch it when you can, but make sure you watch it and then be ready for the discussion on Monday. Okay, so this will be the last video for this week. No recording for tomorrow. And I'm sorry, let me go ahead and start the stopwatch here. That way I stay on task. Um, so no video tomorrow for Christmas, and then that will take us through the weekend. Depending on how far we get today, I'll try not to post a video over the weekend, but let's see how far we get. And then if we have to, I'll post a video on the weekend as well, and then we'll start into Monday. Okay, so please make sure you watch the video. Please make sure you do the work and submit the work through Google Classroom. That way, then I can go ahead and take a look at it. And as usual, please make sure if you have any questions, make sure you email me your questions, and I will go ahead and I will answer them on the video. Okay, so I haven't had any emails yet, so please make sure you watch the videos and email me your questions. Okay, all right. Let's go ahead and let's get started. I'd like to go ahead and start chapter 14 today, but let's finish up with Le Chatelier's principle. I have one correction to make from yesterday, and I apologize for the video for what happened yesterday. So let me go ahead and make that correction really quickly. And it was in terms of the discussion of heat. The correction I need to make was the one that referenced heat and how we can apply Le Chatelier's principle when it comes to heat to determine then the direction a reaction will take. The reaction will take in order to reestablish equilibrium. Okay? So let me go ahead then, and let me go ahead and address that mistake first before we continue on with the discussion with the sample problems that we did yesterday. Okay? All right, so yesterday we were talking about the Haber process. And so the Haber process, remember, is the nitrogen, whoops, sorry, is acting up again. So we have nitrogen gas, okay, reacting with hydrogen gas in a 1:3:2 ratio. So hydrogen gas, okay, to produce for us then ammonia gas. Okay, and so we have then this reaction here. Now I had pointed out yesterday that this reaction is I had accidentally reported to you the wrong value for the delta H for this reaction. And so for this reaction, for the Haber process, this is actually I went back and I checked because it didn't look right to me at first, okay, when I presented you. So I had to go back and check. And when I checked this, then the delta H, the change in enthalpy for this reaction is not positive. It's not positive 92 kilojoules per mole, which I reported to you yesterday, but rather it is negative 92 kilojoules per mole. Okay, so based on this, then remember, based on this, what we can say then, since we have a negative value for delta H here, and remember, this is the change in enthalpy. Delta H is the change in enthalpy. We refer to that as the change in enthalpy. And the enthalpy then, remember, is the amount of heat that is associated with a particular process. And so therefore, we have a, sorry guys, I was hoping that the board will be better today, but change in enthalpy. Maybe slow down my writing, enthalpy. Okay, all right, so with that said then, the change in enthalpy is a way that we can determine, sorry. The change in enthalpy then is a way that we can measure how much heat is involved in a reaction. So heat can either be absorbed or heat can be given off. So if heat is absorbed, then that means that we have a positive value for delta H. That is what we refer to as an endothermic reaction. And then therefore, then we could treat heat then as a reactant. Okay, so if we have an endothermic reaction, heat will be treated as a reactant. Okay, and we'll put heat then on the left-hand side of the reaction here. Okay, for an exothermic reaction, then delta H will be negative, and so therefore this will be an exothermic reaction. So exothermic, and we can obtain these. This is an exothermic process. We can obtain these delta H values. These are all reference values. That means that we can find them online. We can find them in a reference book, and if the reaction is well known and if it's been tested before, a delta H value will be recorded for that particular reaction. Okay, so Because this is an exothermic process, then that means that heat is given off. We can go ahead then and we can include then heat as a product. Okay, so not only will you form ammonia here, but heat also will be given off. And so for exothermic process, we will treat heat then as a product. For an exothermic process, heat is a product. Okay, all right. We have to do that first before we analyze this reaction in terms of Le Chatelier's principle and how temperature affects equilibrium. Okay? All right, so now that we know then that heat is a product here, okay? So if we increase the temperature, so Le Chatelier's principle says then that if we increase the temperature, okay, now remember, an increase in temperature, the changes in the temperature will also affect the values for the equilibrium constant. So not only will the equilibrium shift, but the equilibrium constant will change as well. So changes in temperature will affect the equilibrium constant as well. Okay. All right, so with that said then, when you add heat, when you increase the temperature, what we were essentially doing is that we are increasing the amount of heat. So as we increase the temperature, we're going to increase the amount of heat. And so therefore, for an exothermic reaction, since heat is a product, we are increasing the amount, we are disrupting the reaction, and we're disrupting it on the side of the product. Now remember, Le Chatelier's principle tells us that whenever you disrupt a reaction, whenever you disrupt the equilibrium, that reaction, that process will seek to reestablish equilibrium by making up for that disruption. So if the disruption happens on the right, the reaction then is going to shift and produce more reactant in order to accommodate for that disruption. Okay, so therefore then, if you're going to add more heat, the reaction then will shift towards the left. So it'll shift towards the left. It'll shift left. Okay, and thus we will end up generating more reactants. So if you increase the temperature, you'll generating more reactants. And we saw that with the table that I gave you a few slides back. We saw then that the Haber process, this reaction here, actually the yield, the amount of ammonia that is produced, the percent yield of the ammonia goes down as we increase the temperature. And we saw that. And then we saw then the reverse is also true. So if we want to produce more ammonia, we reduce the temperature, we go to lower temperatures. The reason why that happens is because if you reduce the temperature, what you end up doing is you decrease the amount of heat. You decrease the amount of heat in the reaction, so you drop the amount of heat. And as a result, okay, if you are essentially removing heat, if you want to think about it in that way, if you're going to remove heat, that means then the reaction will shift towards the right. Will shift towards the right to make up for that loss. So this time the disruption here is not adding, but we are removing this some of the product. The product here is going to be heat. So we're removing some of that heat. As a result, the reactants shift towards the right, okay? And thus we will generate more product. So we will generate more product, and this shift then will end up generating more product. Okay. And so at lower temperatures for this particular process here, since it is an exothermic process, at lower temperatures, that means that you lower the temperatures, you will increase the production, you will make more product. And that's going to be true for all exothermic processes. And this generalization right here, and what I've done right here for you, this generalization here works, okay, for all exothermic processes. So for all exothermic processes, and this is for exothermic only, folks. So for all exothermic processes, this will always be true. And so you can imagine then for endothermic processes, then everything will be reversed. So for endothermic processes, and so heat will be on the left here now for endothermic processes. And I would like you to make sure you come up with the summary on your own. If you cannot, please come by and see me, okay? Or I'm sorry, email me and I'll do that for you. But for an endothermic process where heat is a reactant, you can imagine then that if you increase the temperature, that means you increase the heat, the reaction will shift towards the right, generating more product. If you decrease the temperature for an endothermic process, you will remove heat from the reactant side, which means the reaction will now shift towards the left, generating more reactant. Okay, so therefore, for an endothermic process, only these last two parts here will be different. It will be the opposite of it. Okay, all right. So please make sure then that you can come up with this generalization for an endothermic process. But what I have here for you, what I've summarized for you over here in this box, applies only to exothermic processes. Okay. All right. Very good. So with that said, I wanted to make sure I make that correction and clear that up for you. Okay. And so let's go ahead then and let's continue on where we left off with yesterday. And I think we left off with the sample problem yesterday, and I'll save this for you, okay, and I'll post it today for you as well. But let me go ahead then and let's pick up where we left off with yesterday with this the problem involving the two reactions, and we are dealing with volume changes. And so I want to go ahead and use this to review really quickly with you as well. Let me go ahead and share with you the screen here. Let's save that. Let me put that out. Let me share with you the screen here. Okay. All right. So we talked about how volume changes, when you change the volume of a reaction, okay, it basically affects the pressure. Boyle's law. Boyle's law tells us then that the volume and the pressure are inversely related. So actually, when you change the volume, really what you're doing is you're changing the pressure of the particular reaction. So you're changing the pressure. And so with that said, then please make sure if you don't recall Boyle's law, and I'll go ahead and write it here again for you. So if you don't recall Boyle's law basically states then that when you have a gas, okay, Boyle's law, when you have a gas, okay, the volume and the pressure of the gas are going to be inversely related. That means when you change the pressure of the gas, you're going to change the volume as well, but in the opposite directions. That is the essential statement of Boyle's law there. Okay, so when you're changing the volume, as in this problem, that's what we're being asked to consider. Okay, so when you change the volume, so here we're saying that we are reducing the volume. We're making the volume smaller. When this is the case, then that means then what we're doing here is we are lowering the volume. The volume gets smaller. So if the volume gets smaller, according to Boyle's law, what we will essentially do to all the gases here, so we're going to increase the pressure on the gases. Okay? We're going to increase the pressure on the gases by reducing the volume. Okay? All right. So Boyle's law only applies to gases. And so therefore, the changes in pressure, when we talk about Le Chatelier's principle, the changes in pressure then will only affect the gases in the reaction itself. Only the gases will be affected by a change in pressure. Not solids, not liquids, because pressure changes in solids and liquids really don't affect the liquids and solids as much, because they are more dense. They are denser states of matter. And so the change in the volume, the change in the pressure really will not affect the solids and liquids as much. And so for a particular reaction, if there are changes in pressure, we only look for gases. Okay, we only look for the gases. So here, in the very first reaction, we have chlorine is the only gas that we have right here. So when we change the volume, the reaction here will only the change in pressure will only affect the gas right here. It will only affect the gaseous state. Now remember, we said then that when you alter the pressure, according to Le Chatelier's principle, the reaction will shift in such a way where it's going to try to reduce that pressure. So if you increase the pressure, what the reaction is going to try to do is account for that by reducing the pressure. How it does that is by shifting towards the direction, shifting towards the side where there are less particles. Because remember, and I pointed this out to you yesterday, we talked about Boyle's law yesterday, but I also introduced to you Avogadro's law. So what Avogadro's law, and this is the same Avogadro that we named the number after. Avogadro's law gives us then the relationship between the moles of a gas and the pressure exerted by a gas. Okay? So there is a direct relationship between the moles of a gas and the pressure exerted by the gas, which means that you have a lot of particles, there's going to be greater pressure. If you have less particles, there's going to be less pressure. Okay? And so how does that relate to Le Chatelier's principle here? Well, if we're going to increase the pressure by reducing the volume, what the reaction is going to try to do is reduce the number of particles. By lowering the number of particles, you're going to reduce the pressure. Okay? And so we have to count particles here. So that's what the balance equation gives us. And again, Le Chatelier's principle when it comes to pressure only applies to gases. And so if you take a look at this here, we have now 6 gas particles. We have 6 particles on the left-hand side as reactants. We have 6 particles on the left. We have 0 particles on the right, which means then what will this reaction do in order to reduce the pressure? It's going to shift towards the right, towards the side with less particles. It's going to make more of the product. It's going to make more of the product. Okay? And so here then, we talked about this already yesterday, the reaction will shift to the left, shift to the right, shift to the right. in order to reduce the pressure. Okay, less particles. So if you increase the pressure, you need to increase the pressure. The reaction will shift towards the right, towards the side with less particles, okay, and thus reducing the pressure in that way. Okay, all right. So you can imagine then, if you increase the volume and you reduce the pressure, what will happen? Well, the reaction then will shift towards the left in order to increase the pressure. And so with Le Chatelier's principle, we're saying then that the equilibrium will always shift in the direction that will make up for the disruption, the disruption itself. Okay. All right. So let's take a look at the second reaction here. Okay, so for the second reaction then, this time we have all of them are gas particles. We have, so let's go ahead and count total gas particles here. Okay. Whoops, sorry. So we have, again, we got to count total gas particles for reactants and products. Okay, so let's go ahead and let's take a look at that. So on the left-hand side for the reactants then, and this is a balanced equation, we have then two gas particles. We have two particles of the gas. Okay, so we have two particles on the left-hand side for the reactants. We have two particles. And on the right-hand side, we only have one particle. We only have one particle on the right-hand side. Okay, so if we're going to increase the pressure, so again, if we're going to increase the pressure because we've reduced the volume, then the reaction is going to shift towards the side with, again, less particles, which is on the right-hand side. So that means then when you increase the pressure here, the reaction will shift again to the right. It will shift towards the right in order to make up for that increase in pressure. Okay. All right, so that is what you need to make sure you consider when we change the volume. Now, so the volume will also affect the direction the reaction will take, but it affects it indirectly because what happens is by changing the volume, what you've done is you've changed the pressure. Now, make sure you keep this in mind. You can add more particles as well. You can add more particles as well to increase the pressure because Avogadro's law just talks about the number of particles. So if you add more particles in here, then you will increase the pressure. However, the equilibrium will only be affected by particles that, gas particles that are part of this reaction. So for example, if you were to add an inert gas like argon, let's say if you were to add argon to the reaction for this first reaction here. So if you add argon, which is a gas, okay, you add argon gas to this reaction, nothing will happen. Yes, people in the past have argued then, doesn't add the addition of argon gas here contribute more particles and thus increase the pressure? Yes, it does. But the reason why we refer to argon as an inert gas, so this is an inert gas, because it does not react. It does not do anything to this reaction itself. So therefore, because it does not react, it is inert, it will not change the equilibrium at all. It will not change the equilibrium. It has no effect. No shift will occur. Okay? So that's going to be true for any of these gases. So if you add an inert gas, nothing will happen. So the only way that you can affect the equilibrium is one, by changing the pressure. Okay, and the way you can do that most easily is by increasing or decreasing the volume. Okay, but you can also affect the pressure by adding in more particles. Okay, but the only particles that will affect the equilibrium are the particles that are of gas that is actually involved in the reaction itself. So by adding in more chlorine, for example, here, the reaction will shift towards the right anyway, because what will happen is you are changing the number of gas particles. Okay? And so you can imagine that. So as you're increasing the pressure, the reaction will shift right for two reasons. It'll shift to the right for two reasons. One, because you've added more chlorine particles, and therefore the reaction will shift towards the right because of that. Okay? Now, the question, the confusion here then comes in, what about the second reaction here? What if we add in more phosphorus pentachloride, okay, which will increase the pressure, okay, but by adding more, we'd expect the reaction will shift towards the left because you are adding more product. What will actually happen here is that, but like I said, since you're increasing the pressure, you would expect then the reaction will shift towards the right because the pressure, there's less particles on the right. What happens here then is if you add more phosphorus pentachloride, the reaction will actually shift towards the left. The reaction shift towards the left because you've added more of these particles specifically. Okay? All right. So please make sure you ask about Boyle's law, review it, review Avogadro's law. We will talk much more about both of these laws in the second semester. Okay, so please make sure you review those in your first, from the first your chemistry. What I'd like you to do then, folks, is take a look at number 10 in your problem set. This is number 10 in your problem set. Take a couple minutes, read what's happening here, and then determine then what direction will the reaction go in order for equilibrium to be reestablished. Okay? Or is equilibrium going to be disrupted at all? Okay, so take a look at this problem. Take about 2 minutes. 2 minutes to answer this question on your paper. Okay, and then when we're done with this, please make sure you submit it. But on your paper, you don't have to worry about typing it on the Edpuzzle. But on your paper, answer this question here, and you tell me, will the equilibrium be disrupted? And if it is disrupted, in what direction will the reaction take in order to re-establish that equilibrium? Okay, 2 minutes, folks. Go ahead. Okay, well, let's go ahead and take a look at this. So the question then is, first of all, is the equilibrium going to be disrupted? Okay, well, what are we doing here? We are reducing the volume of this particular reaction. Now, remember, if you reduce the volume, if we're going to reduce the volume, the result here then will be an increase in the pressure. Very much like the previous problem. If you reduce the volume, you're going to increase the pressure. So yes, there could be an effect on this reaction if there is a gas involved in this reaction. And here, all 4 of them are gases. So yes, the equilibrium will be disrupted. There will be a disruption in the equilibrium. Now, the question then is, will the reaction shift to the left or shift to the right, okay, in order to reestablish equilibrium? Okay? Well, remember, when we talk about this here, we have to reestablish. What will happen is if we're increasing the pressure, the reaction will shift towards the side with less particles. So the next thing you have to do is you have to count the particles. Okay? So if you take a look at this here, you would say then that it's a 1 to 1 to 1 to 3. So if you would keep it this way here, you would say then that there are 2 particles on the right, on the left-hand side. So you have 2 particles on the left, okay? And you have then on the right-hand side, so we're going to count total particles, gas particles here. Okay? You have 4 total particles on the right-hand side. So based on that, you would predict, your prediction would be then, let's go ahead and do this. Okay? The reaction then will shift. If you increase if you reduce the volume and thus increase the pressure, the reaction will shift to the left. Because it looks like there's less particles on the left-hand side, okay? However, that's wrong. That's wrong, because remember, folks, remember I told you that's not your answer. Because what I told you to remember to do is always, now I was being bad by giving you this problem here, but the point I'm trying to make is always make sure you check for a balanced equation. Okay. Now on the AP exam, I've never, they're bad people. They're evil folks that they stay up late at night. I've shared this before. I feel like they stay up late at night thinking of ways to torment poor AP chemistry students, but they're not that bad. Okay. They won't do this to you. Because if you take a look at this here, this reaction actually is not balanced. A 1 to 1 to 1 to 3 ratio will not be balanced. Okay? Just look at the hydrogens, folks. You have 3 hydrogens on the right here. You have 6, 7, 8, 9 hydrogens on the right here. So therefore, in order to balance this reaction, you have to put a 3. This is a 1 to 3 to 3 to 1 to 3 to 1 to 3 ratio. So it's not 2 particles on the left. Okay, it's not 2 particles on the left that we have here. Okay, it's not 2, but we have 4 particles. Okay, so it's not 2, it's 4 particles on the left as well. Okay, all right. So that's what you got to make sure you do. You need a balanced equation. Why? Because if there's 4 particles on the left and 4 particles on the right, actually there will be, even though we are changing the pressure, there will be no shift. That means then there will be no change. So even though we started out and we expected to have a change here because we changed the pressure, all the reactants and all the products are gases, okay? So we expected a change in this particular problem because of what we learned, but based on what we have here, 4 particles on the left, 4 particles on the right, an increase in the pressure or decrease in the pressure will do nothing to this reaction. So therefore, the only way you can change this reaction here, the only way you can disrupt the equilibrium is by adding more, by not changing the volume. That's not going to do anything to this reaction, okay? But by adding either more product or more reactant. That is how you would change the equilibrium here. Okay, so if you did want to change the equilibrium here, you can't do it by changing the volume. You cannot do it by changing the volume. You have to do it by adding either more reactant or more product. Adding in an inert gas, okay, will not change this either. So adding, if you were to take argon and you add that in, argon again, an inert gas. If you take argon and you add it in, you will change the pressure as well. Okay, so if you take argon and you add it into this reaction here, again, nothing will happen because it's an inert gas. It is an inert gas, meaning that it will not be a part of this particular reaction. Okay, all right, very good. Okay, so the answer then here is that there is no shift, no change in the reaction itself. You won't see anything happen. If you reduce the volume or you increase the volume, you're not going to see any change occur here. Okay. All right, very good. Let's go ahead and let's do one more. Let's do one more problem here, and then I'm gonna let's get started in chapter 14. Okay, so on your paper, then you guys, let me ask you to do this. Okay, how will K change? Okay, so here what we have is they're asking you then what will happen to K. So I give you two different reactions here. I give you the enthalpy. If you notice here, I give you the enthalpy values for both this reaction. What I would like you to do then is take a look at this problem, answer the question on your paper, okay, and take about 3 minutes to do this one, because this time I'm telling you that the equilibrium will change. We know that equilibrium has to change because here we're changing the temperature. Okay, so in this particular problem, you guys, what we're asking, they're asking about equilibrium change as a result of the change of temperature. You change the temperature, folks, you will change the equilibrium. Not only will you change the equilibrium, you're also going to change the equilibrium constant. So with that said, they're asking you here about the equilibrium constant. Okay, so go ahead then, let's take a look at this really quickly. Take about 3 minutes to answer this question, and then I'd like to go over it with you. Okay, so on your paper, let's take a look at how you answer this question. Okay. Okay, let's go ahead and let's take a look at this, you guys. Let's take a look at this. So in each one of these cases here, what you want to do first is identify whether the reaction is endothermic or exothermic. That's the very first thing you want to do before you answer any questions about equilibrium. You answer the question about exothermicity or endothermicity here as well. Okay, so for the very first reaction, we have a positive value for delta H. Positive value for delta H means that this reaction is endothermic. So this is an endothermic reaction. Okay, this is an endothermic process. Okay. All right. For the second one here, you notice that this is a negative value for delta H. So this is going to be an exothermic reaction. So make sure then you, if you have to write it out at first, folks, please write it out. Okay, don't hesitate to do that. But at some point, hopefully, you're just going to look at that and you're going to see and be able to record down that information. Okay. Okay. So next thing you want to do then is identify whether heat is a reactant or heat is a product and add that in. Okay. For an endothermic reaction, then heat is going to be a reactant. So we will find heat on the right-hand side, left-hand side of the reaction here, as opposed to the second one then, heat will be on the right-hand side. So heat can be given off. So for exothermic process, heat is a product. For an endothermic process, heat is a reactant. Okay, so now that we have that established, now we can go ahead and examine what's going to happen here. Okay? All right, so the question's asking us here. If you increase the temperature, so here what they're asking is that we're going to increase the temperature goes up. Okay, so we're going to increase the temperature. We know then that if we increase the temperature, okay, we know then the result of that then is that we will increase the amount of heat. The result of increasing the temperature is that we're going to increase the amount of heat involved in this reaction. So we're going to increase the amount of heat. Okay, we're going to increase the amount of heat. And if you increase the amount of heat, we talked about this, then what happens then? The reaction will shift towards the right. Okay, so the reaction will shift towards the right. Okay, shift towards the right. Shift right. Okay, and in shifting right, then we will generate. If it shifts towards the right, it will generate. More product. It will generate more product. Right? Now, if it generates more product, let's write the law of mass action for this reaction. Let's write the law of mass action because this reaction is asking us about equilibrium constant. Okay? So let's go ahead and write out the law of mass action. Let's write out the equilibrium constant reaction for this reaction. K then is going to be equal to the pressure of NO, nitrogen monoxide, pressure of NO raised to the second power, all over the pressure of nitrogen times the pressure of oxygen. Oops, sorry. pressure of oxygen. Okay, so that's the law of mass action here. So in a 1 to 2 ratio, it does work. It's all balanced out. Okay, all right. So if you increase the temperature, you're going to increase the amount of heat. Okay, that means you're disrupting the left-hand side. And you're increasing the left-hand side, then the reaction will shift towards the right, producing more product. You're increasing the numerator here. So if you're going to increase the numerator here, what will result from this then? K, and let's go ahead and take a look at this. What will happen then? K goes up. You will increase K. K will increase as a result of changing the temperature. And that is how you would track this. Okay? So this is the way that you would hopefully be able to answer it. Okay, so the answer then is K will increase. Okay, so you'll have an increase in K, but this is the reason why K increases. Okay, so make sure you're able to follow that. Okay, starting with determining that endothermic, looking, and I'll go ahead and write it above here. Okay, so starting out with the example, starting out by identifying that it's endothermic. Okay, then as a result of that, now we're talking about, then we go ahead and take a look at what the disruption is. The disruption is an increase in temperature, which means that we have increased amount of heat. Okay, so that's the disruption right here. Since heat is a reactant, the reaction now will shift towards the right, making more of the product. Okay, and as it produces more product here, it's going to change the equilibrium constant by increasing it because you're increasing the numerator. Okay, all right. Very good. Let's go ahead and let's take a look at what happens with the second one. Okay, so let's go ahead and take a look at the second one. And if you see this on the exam, okay, if you see this question on the exam, you can write it out exactly the way I have it written here. That's a perfect summary and a perfect answer for what we have here, okay, without using too many words. Okay. All right, so for the second one, also, we are still increasing the amount of, so we're increasing the temperature. So that doesn't change. So we're increasing the temperature. That increase in temperature will lead to an increase in the heat. So the first two steps here will still be the same. So you're going to increase the amount of heat here as well. Okay, so we see an increase in heat. Okay. However, this is where the similarity stops between the first two reactions here. Because for the second reaction here, this is an exothermic reaction, which means that heat is on the right-hand side. So if you increase the amount of heat, you are disrupting the reaction on the right-hand side. Therefore, according to Le Chatelier's principle, the reaction will shift back towards the left. Okay? So we have a shift to the left, okay? Not a shift to the right. It's going to be a shift to the left. Shift to the left. Okay? Which means then you will generate more reactant. Okay? So instead of generating more product, you're going to generate more reactants. You're going to generate more reactants. Okay. Okay. And so what will happen to K as a result of generating more reactants? So let's go ahead, write out the law of mass action for this reaction here. Okay, so let's write out the law of mass action for that reaction. So K then is going to be equal to the pressure of sulfur trioxide raised to the second power all over the pressure of sulfur dioxide raised to the second power. And I'm sorry, these should be Kp. Okay, so Kp for each one of these here. Okay, times the pressure of oxygen raised to the first power. Okay, so that is law of mass action. So if we are going to shift the reaction towards the left, thus making more reactants, you see then that we're going to be increasing the denominator here. We're going to be increasing the denominator, and as a result, what we end up generating is what ends up happening is that we will be the equilibrium constant will get smaller. So we see then a decrease in the value. Oops, sorry. I see a decrease in the value for K. Okay, so the K value for the equilibrium constant will drop as will get smaller as a result of that. So this is then the summary that you can use to describe what happens with an exothermic reaction when you change the temperature. Okay. All right. All right. Very good. So please make sure then you take a look at this here and practice the problems from chapter 13. I think this would be set D from chapter 13. And please make sure you ask about them. And if you email me a question about these here, then I can work out one of the problems for you in the next video. Okay. All right. So with that said, folks, that is it for. Let me go. that is it for chapter 13 and equilibrium, for the introduction to chemical equilibrium. What we're going to do here now, folks, is we're going to apply what we know now about chemical equilibrium, okay? And we're going to apply that now to acids first, okay? And then we're going to apply it to determining solubility. We're going to use the equilibrium constant. The idea now that we're going to use the equilibrium constant in order for us to determine then, to make some assessments about some other chemical processes. So we're going to start out with acid-base chemistry, okay? And we're going to apply what we know about equilibrium and the equilibrium constant now to acid-base chemistry. And then we're going to apply what we know about equilibrium to solubility. Okay, so we're going to talk about the acid-base chemistry first, then we're going to talk about solubility. So chapter 14 here is going to be about acid bases. And then hopefully we can get this done and we can start when we get back in January on the 5th with solubilities. And we can determine then, we can go ahead and use equilibrium constants to determine then the direction in which a process will take. We're going to start out then, first and foremost, with determining how that affects acid-base chemistry. And then what we'll do then is, let me go ahead and do this. And then we're going to apply our understanding of equilibrium to determining solubility. Okay, that is determining then how a solute will or will not dissolve in a solvent. Okay, and so we're going to use equilibrium. Equilibrium is an especially important concept, and we talked about this earlier. Especially important concept to understanding how chemistry works, how the universe works. Okay, and so hopefully with that introduction to equilibrium, you can go ahead and apply it now. So let's go ahead then. Let's talk about acids and bases in general first. Okay, so let's go ahead and let's quickly just review the nature of acids and bases. So acids and bases are all around us. Okay, we make use of acids and bases all the time. We essentially are a collection of acid-base reactions that take place in us. Okay, we may not recognize it, but it is. Okay, we will. So acids and bases are very important chemical compounds that are needed for our survival and needed for our civilization, for our society now. Acids and bases are integral parts of everything that we do. Okay? And so they're different. They obviously have different properties, and we'll talk about the different properties as well. But do make sure you understand then that certain properties of acids and bases that distinguish them sometimes are not as straightforward as we'd like. I mean, we can measure pH. pH is definitely a good way to describe an acid versus a base. Okay? But like I said, the properties here of acids and bases will vary as well. You have the strong acids, weak acids, strong bases, weak bases. Okay? But with that said, though, I think there are some general characteristics that we can use based on the definitions that we will use to describe what acids and bases are. And there were three definitions that we talked about that you learned about back in first year chemistry. We talked about how we can define acids and bases according to the Arrhenius acid-base theory, which is the very first one here, the Bronsted-Lowry acid-base theory, and then the Lewis acid-base theory. We're not going to delve into the Lewis acid-base theory so much here. That's a little bit more advanced definition of what acids and bases are. But essentially what we have here is that we are defining what acids and bases are in terms of their chemical properties, okay, and in terms of what characteristics they have chemically. Okay? So let's go ahead and let's talk about the Arrhenius acid-base theory first. I'm not going to spend too much time on this because we talked about it before. Arrhenius proposed then that a very basic and simple definition of what acids and bases are. Okay, so essentially for Arrhenius, the acid is any substance, any compound that will produce a hydrogen ion. Okay, so that's how he defines an acid. Okay, so if you take a look at any acid, that acid should have a hydrogen ion when it is in solution. Okay, when it's dissolved in solution, it should generate a hydrogen ion. A base, on the other hand, then is any compound, any substance that will produce a hydroxide ion. Okay, and so examples of an Arrhenius acid and Arrhenius base, Arrhenius acid and Arrhenius base. Then let's go take a look quickly. Okay, so an example of an Arrhenius acid, Arrhenius base. Let's go ahead and take a look at this. An acid then can be seen then as, say, for example, hydrochloric acid. Okay? And it's going to be HCl. And we're going to write that as an AQ because it's in solution, in a water solution. Okay, and the reason why this is an acid then is when we dissolve this here. Okay, what ends up happening is that we produce then a hydrogen ion and a chloride ion. Okay, now with an example of an Arrhenius base then. Okay? An Arrhenius base then is, for example, sodium hydroxide. Okay? Sodium hydroxide, when it is in water, dissociates completely to form the hydroxide ion here and the sodium ion. Okay? So the Arrhenius acid-base theory is the simplest acid-base theory that we have out there, because we can just look at the compound and make some determination about whether the compound will produce a hydrogen ion or whether it will produce a hydroxide ion. Now be careful about this, because not all compounds that contain hydrogen will produce the RRR acids. So for example, if you take a look at methane here, methane is not an methane is not an acid. It's not an acid. Why? Because when you dissolve methane, first of all, methane will not dissolve in water, but methane here will not produce for you any hydrogen ions. So the basis of an acid, according to the Arrhenius acid-base theory, is that it has to be able to produce a hydrogen ion. So let me go ahead and show you how that works. Okay, so let's take a look at the hydrochloric acid here. Okay, so with hydrochloric acid, what happens then is when you add hydrochloric acid into water, okay, when you take a look at this here, okay, that's what that AQ means. What hydrochloric acid does is it breaks up into hydrogen ions, okay, and chloride ions. So this is why HCl is going to be considered an Arrhenius acid. Okay? Sodium hydroxide. The reason why it's considered an Arrhenius base is when you dissolve sodium hydroxide in water, you will end up with sodium ions, okay, and hydroxide ions. Okay? And so it's the production of this ion here that makes the HCl an acid. It's production of this ion here that makes the NaOH a base. And that is as simple as you can get. You don't need to know how these interact with other compounds. You don't need to know about the reaction. You just need to be able to identify whether this process occurs or not. That is the dissolution. Okay. Does the substance dissolve to form hydrogen ions? Does the substance dissolve to form hydroxide ions? And if it does, then you have an acid and a base respectively. Okay? Easiest way to determine acid and base. Okay? So that's the Arrhenius acid-base theory. The problem with the Arrhenius acid-base theory is that it's fairly limiting. It's not as broad as we would like it, because there are other acids out there. There are other types of acids out there that don't necessarily, that aren't going to necessarily produce for you a hydrogen ion or produce for you a hydroxide ion. Okay? And so that's where the Bronsted-Lowry acid-base theory comes into play, and it's able to make up for that. Now understand this, the Bronsted-Lowry acid-base theory is a more complex theory, but it doesn't negate, it doesn't contradict, it doesn't refute the Arrhenius acid-base theory. It adds to it. It expands upon how we define an acid and a base. It broadens that definition of an acid or base. And so the same thing holds true for the Lewis acid-base theory. The Lewis acid-base theory is much more comprehensive than the Bronsted-Lowry acid-base theory, because now it discusses an acid and base and defines an acid and base in terms of electron motion, okay? Gaining or losing of electron. Okay? And so that's why we still use these acid-base theories, and we will use them in combination with one another, because what we can do then is we can see that these acid-base theories complement one another. They don't do away. Okay. All right. So with that said, then, with the Bronsted-Lowry acid-base theory, it broadens the definition of an acid by saying then that an acid is one that donates a proton. Now, the term proton refers to a hydrogen ion, okay? And the term proton is used typically for hydrogen ion for one very simple reason, you guys, because imagine this. Now, with the hydrogen ion, remember you have a proton in the middle and one electron out in the nucleus, outside. Okay, so when the electron, for this is hydrogen, okay, and so that's neutral hydrogen here. So for this to form, the hydrogen ion to form, what happens is that electron has to leave. When that electron leaves, what do we end up with? We end up with a simple proton. There it is. And that's why we refer to the hydrogen ion then also as a proton, because that's all we have left. So you'll hear me refer to this as a proton. I'll also refer to it as a hydronium ion. We'll see why in just a moment. Okay, but this is what the term proton means. So an acid, according to the Bronsted-Lowry acid-base theory, is any compound that will donate a hydrogen ion. Okay? And so with that said then, for a base, Bronsted-Lowry defines the base then as any compound that will accept a proton. So when we take a look at the Bronsted-Lowry acid-base theory, we are not looking at individual compounds. So the Arrhenius acid-base theory, we just look at the compound. We isolate the compound. We ask ourselves, does that compound contribute a hydrogen ion? Can it contribute a hydroxide ion? And if it can, it's either an acid or a base. However, to define a Bronsted-Lowry acid-base theory, we have to look at that compound in the context of a chemical reaction. The Bronsted-Lowry chemical acid-base theory will only be effective if we can look at how a compound interacts with another compound in the context of a chemical reaction. Okay? So that's what you need to make sure you keep in mind. So with that said, then I give you this reaction here. Okay? Now we already know then that I'm sorry, I'm running out of time. I'm running out of timer. We already know then, I already told you up top that HCl is an acid. We're going to see why it's an acid now. Okay, so I'm going to go ahead and I'm going to write this in here. Okay, so that's an aqueous. And we're going to see how it interacts with water. We're going to see how it interacts with water. And water, we don't really think of water as being acid or a base, but according to the Bronsted-Lowry acid-base theory, we can define it as an acid or a base. And so this is where we're going to pick up with and I will, since we are a little bit behind, I will go ahead. I will post a video for you over the weekend as well. So I'll try to post it by Saturday afternoon. So you can go ahead and watch that. Okay. But I'll post that for you. Please watch it. And on that video, then we'll pick up where we left off here. We'll talk about the Bronsted-Lowry acid-base theory. Okay. So I hope you folks have a very Merry Christmas. I wish you the rest, and I hope you guys enjoy that time with your family, and I will stay safe, you guys, and I will see you guys on video this Saturday. Okay, Merry Christmas, you guys. I'll see you.